Hi, in today's video, we're going to look at using a microphone on an ESP32 and process the data using Fourier Transformation and display it on an LED. We're going to apply two different methods, the software-based Fourier Transformation and hardware-based MSGEQ7 to process the data and display it on this LED. In today's video, we are going to look at how we can process some kind of a signal which decays over time. So this could be something like an audio signal. So basically, this actually forms some kind of a wave kind of a signal. And what we want to do is do a Fourier transformation and get the frequency. So in case of an audio signal, you can deconvolute each frequency out of the recorded signal using Fourier transformation. So in Fourier transformation, what you do is you do the integration of this g of t function, exponent to the power minus 2 pi I times the frequency times the time. And what you would notice is that what you're doing in the Fourier transform is converting this axis that is in seconds to 1/2. So frequency here is a 1/2. So that is what you're trying to do in the Fourier transformation. And if you want to learn more about this, I'm going to leave the links below. And this is a beautiful video done by 3 Blue 1 Brown. Go and subscribe if you're interested in these kind of topics. And here, this person tries to explain how you can actually do this kind of Fourier transformation for various signals and deconvolute out their frequencies. The human ear can listen from somewhere from 20 hertz all the way to 20,000 hertz. Dogs have a much wider range, so they go from 20 hertz all the way to 45,000 hertz. So they can hear sounds at much higher frequencies as well, which is kind of very interesting. And here, what we want to do is actually get this audio signal as a function of time. And for that, what we're going to do is we're going to do fast Fourier transformation, which is a library written for Arduino by this particular person. And we're going to do a definite integral. So definite integral is you don't do an integration from minus infinity to plus infinity except from time t1 to t2. So t1 is the time at the starting of your signal acquisition, and t2 is the time at the end of your signal acquisition. And the difference between that is your sampling time, and your sampling frequency is usually 2 times the frequency that you're trying to look for. So this way you get one signal on the top and one signal on the bottom, and you scan it high enough that you should be able to deconvolute out the signal that you're trying to do your Fourier transformation. You have a digital signal and you want to measure the voltage that comes in as a function of time. So basically this is an ADC value that you're trying to measure, and the number of samples is limited by how many times you can get your ADC measurements. So here, once you get these measurements for a particular number of samples, then you do something called a fast Fourier transformation, and then you can deconvolute out the frequencies. But there are a few limitations for microcontrollers. So basically that would mean that the sampling frequency must be really high. That is, it should be around 2 times of what you want to measure. So 2 times of highest value here is 20,000, which means if you want to measure this, you want to sample at 2 times that, so at around 40,000 hertz. And then the sampling time should not interfere with other functions like Wi-Fi, serial, and other things that a microcontroller does. And fast Fourier transformation calculations are CPU intensive, so you would want to use a much faster microcontroller, and frequency binning needs to be done manually. So that means that if you want to put it into different bins, you want to read all these values, put it into bins, and then you can do any kind of processing. In my experience, ESP8266 is not able to satisfy all of these things. That is, I'm not able to sample quite frequently in order to actually do a real-time Fourier transformation on all the frequency range that I'm able to hear. And ESP32 actually is a very good candidate to actually try these things out. Here, I'm just going to show you how we're going to do this using the software Fourier Transformation. So in the software Fourier Transform, all you require is a microphone, and this microphone has an automatic gain control. So basically what you need to do is when you tie this gain to ground, you have a gain value of somewhere around 50 dB, and that is good enough to give you a good signal, and that signal is generated out of this blue line that is connected to the VP pin or GPIO 36, and this one is 3.3 volt compatible microphone. And what you do is then collect a few amount of your data, and then we would do the Fourier transformation and put it into these bins. We actually sample through different frequencies all the way from 20 hertz to 20,000 hertz. Most of this code has been borrowed from this particular user, David Bird, who does a great job in actually sampling this particular data set and doing a Fourier transformation and binning them into these different bins. So because the iPhone's headphone doesn't have a good frequency range at around 16,000 hertz or beyond, I just bin the first 7 bins. So that is what you're going to see. And in order to actually visualize it, I just connected a WS2812 LED where the ground is connected and GPI 12 is connected to the data line, and I power both of these using 5 volts. So here you will see this particular video where we actually see the response of these 7 different bins. In order to do a hardware Fourier transformation, we could use something like a chip. So this particular chip is MSGEQ7. So there are 8 legs. So you power this chip using the legs 1 and 2, and the output comes out of pin 3. And this is a strobe pin. We'll come to that, what it does. And this is the input, and the input is usually in series with a capacitor and a resistor. And then the pin 6 is connected to ground using a capacitor. Pin 8 is actually the clock. So in order to for this pin to function, you require exact value of 33 picofarad capacitor and a 200 kilo ohm resistor in this particular configuration, and you connect the pin 7 to actually reset pin. So when you look at the data sheet of MSGEQ, what you will see is that you have to go high and low in a particular combination of this reset and strobe in order to get these values out of this ADC in different bins. So here the input actually comes from the microphone, it is processed here, and you send the signals on these 2 pins, the reset and strobe, and that will actually give out these values out of these particular bin into a GPIO, and here you just use an ADC to actually read these values, and then you can then go ahead and display this. Again, we use the same concept, except here we connect the LED pin to pin number 12 and the common ground, and the 5 volt we power both our LED and here. So here we're doing the exact same thing, except that we are using this chip to do the job. And again, here you're limited to the capability of this chip, and this chip has these bins and you can't move around, but this is a very good binning region for the audible frequency, so you can go ahead and see what it does. Here again, we're going to sample the audio signal all the way from 20 hertz to 20,000 hertz on an Apple iPhone's headphone.